Good morning, good evening, good afternoon to everybody joining. Thank you so much for taking the time to join us today. So today I'll be talking about with Dhruba about real-time analytics on computer vision data. So just to give you a brief background, I'm Tushar. As Alex has introduced, I'm an engineering manager at Standard Cognition. We build autonomous checkout. I'll talk a little bit about that later in our presentation. I also want to introduce Dhruba, who is the co-founder and CTO of Rockset. Maybe Dhruba can just say hi.
Hi, guys.
Yes. So with that, I'll directly start diving into some of the content. So just to give you an overview of what we'll be talking about today is I'll start off with talking about some of the data challenges in computer vision. Then I'll be touching upon some of the data stack pieces for us at Standard Cognition. And then Dhruva will be talking us through more about how Roxette is applicable to some of the computer vision data that we are processing here at Standard Cognition. And then we'll leave some time for Q&A. So with that, so just to give you a quick background on what is computer vision, like computer vision has a lot of terms and a lot of people define it differently. But computer vision is just the aspect of taking some camera stream of information and processing it to get insights about the world around us. So just to show you like what autonomous checkout is. So this is one of our videos of something that this is a glance at our product. So I'll just play this video. So here you can see there are different items that are there in a retail shelf, and you need to solve for a lot of complex problems. So so you start with like, okay, I can grab one item. You need to know who is grabbing the item, what the item is. And you're kind of doing this from very few camera perspectives. So understanding, like even as a human, it's very hard to see what exactly that person there is picking up. And then the other part of the problem is you need to do real-time scene comprehension. So you're not just trying to understand what are the items this person is picking up, but where is this person in the store? What items are they holding? What items are they passing along? So the ability to get all of this right is very hard because as a customer, you're comparing your user experience to something which you already do at a store where you pick up certain items and then you get all those items billed in most cases correctly. So you're expecting something similar from an autonomous checkout system. And not only that, once you do all of that, you have to generate a receipt. And that kind of adds another constraint that you can't do this like YouTube analytics, which the analysis can come in like 15, 20, 30, an hour late. But with computer vision applications in production, you really need those insights really quickly. So latency is a very important consideration when you talk about any computer vision application. So two of the key challenges in actually three challenges that we face in computer vision is data volume, velocity, and data reproducibility. So talking about data volume, if you think about a raw sensor generating an image stream, it typically generates an image stream from anywhere between 1 frame per second to 120 frames per second. And each raw frame typically generates around 40 megabytes of data. So anybody who's used a DSLR and shot in RAW, you will see that the raw image is really massive. And I think that's very critical because you can learn a lot more insight from raw pixels versus compressed or derived pixels. So it's important to think about it when you have access to raw data, why not use it for your machine learning application? So with that, with data being generated at that rate from the camera itself, you get into these derived outputs, which could be a model running for item detection, a model running for item tracking, a model for theft tracking. And each of these models like output tensors. And these are also around like 10,000 to 100,000 like floats per frame. So these are just like prediction weights that each model is generating every moment as it's processing this stream of image and video content. And on top of that, you need to generate like something about what was picked up from the shelf, what is in the cart of the shopper, and even is there theft happening, right? So you're trying to analyze all of this information from hundreds of cameras at a rate of like, so this data volume suddenly becomes so massive that you have to process it fast enough. Otherwise, you can't even write so much data to disk. You can't serialize every single data stream to disk. It's almost impossible to write this volume of data. So with about 100 cameras, you can see that you generate around 400 GB of data per second, assuming a 30 frames per second camera. So the volume of data really rapidly scales very quickly, and you need to process this really quickly. So the other challenge is data reproducibility. And by data reproducibility, what I mean is it's almost impossible to recreate the exact same shopping scenario that you will encounter in a store, because each of those shopping scenarios is very unique to the shopper and the type of shopper and the type of experience. There might be someone who just wants to go in, buy 2 items and walk out. There might be a shopper who spends an hour at the store, picks up 3 items and then leaves. So there are a large variance in the types of shoppers. There's large variance in the types of items that are sold at different types of stores. And there's variance even in the speed of movement. So just thinking about generating video streams from hundreds of cameras, taking all of these parameters into account, quickly becomes a problem that's very hard to scale. So with that, it's really impossible to just reproduce different types of shopping behavior in a lab. So you really need to get ahead of yourself and start observing production data the faster you can. So I want to talk a little bit about the data stack for standard cognition. So one of the key challenges in computer vision data is you want to give the developers the ability to build and customize models based on production outcomes to ensure accuracy, right? You don't really want, you trained some model, you got some results on your validation set, you think the model is good, and then you ship it to production. And after that, you're like, okay, this model is not actually performing the way I expected it to perform. And then you need to make a tweak in the model, you need to make a tweak in the training data. So that iteration is very long. So it could take anywhere between 3 months to 6 months. So the cost of making these changes is so massive that unless you have clarity on why you're making these changes, it doesn't make practical sense to just keep training the model with another set of inputs. You really want to truly understand what are the problems that this model is actually facing in production. So you start thinking about what are the requirements of a data stack for computer vision, right? So there are different teams involved, right? So there's an infrastructure team that's handling a lot of the on-prem data processing, which includes handling tens of terabytes of data and gigabytes of data per second. So they are thinking about, how do I handle all this data? How do I process it rapidly? How do I just generate insights from this data rapidly? How do I run models on this data rapidly? And then that data that is being processed at the infrastructure layer gets fed into application developers. So what the application developers are trying to do, they are trying to join these different streams of data and try to make a decision which is more predictable for the end user. And it's not just the application developers, it's also the platform developers who are trying to build out APIs on the data and make this data available rapidly to the application developers, so that the application developers can just use that information to start building application logic around all the computer vision processing that has happened prior. And not just that, you also want to be able to analyze how your model is performing and what is the behavior of the model in production. So you really need to support a data science use case as well. So if you think about one of the use cases that comes to my mind first is like, how do you do theft detection at a retail store with all of this data, right? So you're almost analyzing around 700,000 data points in a short span of like 5 minutes. Each data point is about like 30 bytes, and you're generating data at a velocity of about 20 megabytes per second, right? And these are 700 data points, which are all derived data. These are not even actual This is not just the raw image data, right? So that has already been processed. So if you're building something like a theft detection microservice, you need the model to predict certain things. You need to build a secondary model which analyzes those inputs. And once you have a good enough model, you want to deploy it to production and notify the store manager or someone in the store that there is a theft happening right now, right? Because with theft, it's important to know that the theft is happening right now. A lot of stores have security cameras, but by the time they know that a theft happened, it's too late, right? So I think that kind of is a use case, one of the use cases we've been investing in at Standard Cognition. So what is the data stack for computer vision application development look like, right? So you can think of it as we use Google Cloud as our preferred cloud vendor. The reason for that is if you work with retail, you don't want to work with Amazon. That's kind of very obvious. And most retailers don't prefer, even if you're a vendor to them, to use AWS. So that's part of that choice is very simple. Like, let's just use Google Cloud. But thinking about what exactly you want to do is you want to be able to process this data really quickly without incurring the cost of doing a full scan in something like BigQuery. So BigQuery, even though you might say, okay, all of this data is in Google Cloud, you can just connect it to BigQuery and start running some queries against it, right? So there is a cost benefit trade-off where is it worth, like if the volume of data is so much, every scan is, you're probably scanning like terabytes or petabytes of data very quickly, right? And even though that will scale, you will run into costs which are like prohibitively expensive to get the kind of insights that you are trying to get out of this. And then you can think of it like, okay, once you get all of this data into Rockset, you're looking at ways to quickly explore this data by using SQL or any of the other Rockset clients, or even importing it in a Jupyter notebook and starting to do some ad hoc analysis on that data. So once you get to that point where you've done some ad hoc analysis, you really want to now think about how do you deploy this application and deploy this to production. And then that's where you can build out a query Lambda quickly in Rockset and then just have it available for developers to integrate into their applications. So with that, I wanted to hand it over to Dhruva, who will talk about Rockset.
Hey, thanks, Tushar. Thanks a lot. So I am going to tell you a little bit about Rockset data stacks. That's the data that plays a very core part in some of the processing that Tushar mentioned, how you can process a lot of data at very fast speeds. So Rockset is an indexing database, and it is built for application developers who can actually make text queries, who can do searching, who can do aggregates and joins on a lot of their latest data. And this is data that is maybe vision data, maybe photos data, or maybe any kind of analytics data that's coming out from your AI or vision streams. Can you go to the next slide, please, Tushar? So there are many different uniquenesses of Rockset, but I'm going to touch upon 3 or 4 of the main ones, because these are the ones that are really important for processing high volume vision data, right? The first one is how fast can Rockset ingest data and make it queryable? The second one is how can application developers get like low data latency and low query latency for their data set? And then how can you build an application platform for vision developers who might not know much about the data but can write applications, programs? So you need to enable a lot of application developers to be able to process, to be able to use that data. And obviously, then you might need full-featured, lot of complex type of queries that your system needs to handle. So Rockset does all of these 4, and I'm going to explain how each one of them happens. And these 4 are kind of the basic building blocks of a vision data stack that you might want to build. If we go to the next step, so high ingest rate. So Rockset can process a lot of data. Again, this is metadata that you extract out of your vision data. Let's say you have a video stream, you can extract metadata out of those. And then you can put them in a database where applications can query. So the ingest rate for a system like Rockset is very high, gigabytes per second or terabytes per hour, or you can think about very high volume data set. But you don't have to schematize this data, or you don't have to write any code or scripts to do this. It's automatic. You can point if your data set is coming from a Kafka source, or it's coming from Google Cloud Storage, like Tushar mentioned at Standard Cognition, you can just do point and click, and it will automatically get indexed into the Rockset indexing database. Also, the formats of vision data. Some vision data might be in JSON format. Some third-party data sets that you want to join with might be in XML. And Rockset understands these formats, all of them. So you don't have to do anything, any customization or code for yourself. You can just point and click, and now all your JSON data is queryable in Rockset. Rockset supports all these formats like CSV, Parquet, and other data formats that are quite popular in some of these vision data sets. If you go to the next slide, please. So the two main reasons why it's useful to some of the application developers at Standard is because Rockset has very low data latency and very low query latency. So the data latency is the time when your data is captured or processed. The time delay between when your data is captured by your source and, let's say, by the time you actually make intelligent decisions on this data. That's the data latency. So for example, the theft monitoring system that Tushar mentioned, for that it's very important to reduce data latency, because the earlier you can make decision on your data, the more business value you might be able to add to your business users. So Rockset is well built to reduce data latency, because again, Rockset doesn't need you to do any ETLs or cleaning. You can access raw data as and when it is produced. And typically these data latencies are a second or maybe 1 or 2 seconds at the most. You don't need to write any ETL scripts. You don't have to clean your data and do more pre-processing before you can query this data. So again, Rockset lets you reduce both of these latencies, because you can query JSON data immediately as soon as it is produced. There is more information on how we do it in the Rockset website if you want to check it out there. The third reason that Standard or application developers at Standard likes Rockset is because Rockset has this concept called query Lambdas. So these are it gives you a very serverless way of building your applications. Let's say your application has 3 microservices, like an inventory microservice, or an item tracking microservice, or a theft detection microservice. Now you have different application developers working on these microservices or building these microservices, and they get complete isolation from one another, although you are working on the same database. And these application developers or let's say you are building some complicated models that you want to run in production, you can encapsulate those models in a query Lambda, and the query Lambdas expose a REST endpoint, and your application developers just hit the REST endpoint to get their job done. They don't really need to understand very complex SQL logic that is encapsulated inside these Lambdas. So this is a great way for a company or an enterprise to build a very nice developer platform for all their developers. And then the fourth one is that Rockset supports SQL, which means that you can do complex aggregates, joins, and group bys, and relevance. Again, I'm not saying all application developers like SQL, but if you want the full expressive power of SQL, you can always use a standard SQL language with Rockset. Again, Rockset is JSON in and SQL out, which is kind of the best of both worlds, where there's a NoSQL database and a SQL database. And if you don't like SQL, you can encapsulate this SQL inside your query Lambdas and have your application developers hit the REST endpoints using query Lambdas to do their microservices. So those are some of the reasons. Please feel free to go to the rockset.com website and check out more details there. I think, again, if you kind of summarize, there are 3 or 4 reasons why Rockset is useful for application developers here. It makes you make fast queries and make your application developers move very fast. So I'll rest my case here, and I will see if you have any questions, or both me and Tushar maybe can help answer any of the questions you might have. So I see one question. Does Rockset support data in knowledge graphs, ontologies, OWL, RDF? That's a great question. So Rockset essentially is an indexing database where you can put in semi-structured data on one side, and you can get SQL on the other side. So now the question is that for building a knowledge graph, if you can kind of think about a knowledge graph as a set of JSON documents where one field in a JSON document could refer to another field in another JSON document, and you can think about it as a graph, then yes, you can actually represent your knowledge graph in a JSON format using documents inside your JSON database, and then you can make SQL queries to gather intelligence. Rockset is not something where it's great for building data models. It's great for actually serving these things in production. So like Tushar mentioned, it's a great system where you want your application developers to look at raw data. So it's not like somebody's building and refining a knowledge graph and then publishing the knowledge graph to another set of developers. It's a way to actually expose a lot of your raw data to all your developers who can do different things using the same database. So some of them could be building a knowledge graph if they want, but some other people could be serving real applications on this data. There's one more question, I think, maybe Tushar can help explain. I think somebody asked why GCP versus AWS.
Yeah, I can take that question. So I think the only reason is business reasons. Like if you work in the domain of retail, nobody wants to pay money to Amazon. That's just the only reason. So that's a simple choice in that sense to choose GCP versus AWS. I think there are obviously ecosystem benefits of AWS that you don't get by choosing GCP. But overall, I think from our experience, Google Cloud has moved the needle quite a bit since in the last couple of years in terms of feature parity with AWS and in terms of what ecosystem they support is works really well for us. And another thing I wanted to point out there is most of our processing is not happening. There are some parts which are happening in the cloud, but a large part of the processing happens closer to the actual place where this data is being generated, because the latency and bandwidth costs are very, very high. So we don't in a lot of our use cases, we actually prefer not to use the cloud as much as possible. So that's for a cost, just for pure cost reasons.
Yeah, that's a good point that you mentioned. So Rockset is a completely cloud service, which means that you don't have to install anything, which is why it makes your developers move fast. But like how Tushar explains, there might be reasons why you want to put some data on-prem and some data in the cloud. And there's one more question. I don't know whether I have time or not, but I think Salim asked this question. I think he says it's cool to having separate APIs like this. So I think he's referring to Lambdas and SQL APIs, I'm guessing, right, Tushar?
Yeah.
I see that.
Yeah, so I think, yeah, so on that APIs point, I can talk a little bit. So I think one of the big values is you have this data and you usually in a startup, you don't have fully staffed backend teams, fully staffed data engineering teams, fully staffed deep learning teams either. So you really want to be able to take everything that you're generating and make it as production ready as possible, right? And with this, you don't have to even staff that team, right, in the short term. And in the medium term, as your application logic keeps evolving and you get into more stable APIs, you might want, so you kind of can defer the problem to a future where you don't get as much as many queries, where you can just put up a query Lambda and say, okay, yeah, this will work and this can scale. I don't need to worry about it. And the data that I'm ingesting into it can keep changing without understanding the schema. And then I can just edit the query Lambda and say, okay, point to this new collection or run this query in a slightly different way. And that just works. You don't have to worry about things there. So
cool. Hey, thanks for explaining that, Tushar. I think we've run out of time. So thank you. Thanks a lot to everybody.
Yeah, thank you so much, everybody. If you have any questions, feel free to ping us through the Hopin platform or on the Rockset community Slack.
Yeah, the slides will also be there in rockset.com/resources, maybe by tonight or something. So please take a look there. I'm trying to see if there's any other questions. No questions. Cool. All right. Thank you. Thanks a lot.
Thank you, everybody. Bye.
Bye.